proceed.
Thank you very much. Very briefly, by introduction, I represent the digital solutions function in Orica. We look at the digital enablement of blasting, but of course going upstream into ore body knowledge, downstream into measurement, and connecting through to simulating all the way downstream to the output of milling, which is where my colleague Nick, who's also on the line. Nick.
Hi there. So did you just want me to introduce myself briefly?
Yes,
Angelo?
just very quickly. Thank you.
Yeah, so my name is Nick Beaton, and I work for the Cooperative Research Centre for Optimising Resource Extraction. We work very closely with our participants, one of whom is Orica, and the integrated extraction simulator that we developed is both a simulation and optimisation tool for looking at the value chain all the way from blasting through to final concentrate.
Thank you, Nick. To open up the session, I'm just going to move on to an overview slide. The nature of the way that we'd like to conduct the session, of course, is quite conversational. You have the ability to chat or raise questions. Please feel free to do so. I can't quite see when the chat's coming up, but if the facilitator or perhaps Nick can assist, we'll take those questions as they come up. To introduce the session, mine to mill is a technique that's been demonstrated a number of times in operations across the world to unlock value through mill throughput optimization and increasing MPV of the extraction of ore bodies. However, it's also almost universally true that mine to mill tends to occur on a project basis. So there's enormous organizational effort and intensity involved in getting such a project going, getting the mining and the milling teams to work together, and then in managing the day-to-day operational workflow needs from scheduling through to blasting, mining, and of course through to the process plant. Consequently, our observation is that mine to mill tends to have a bit of a lifespan, after which that organizational effort is too much, and the mine to mill initiative tends to fade back into conventional operations. So a challenge of the era is to make that sustainable, to make operational workflows a reality in mine to mill. But fortunately, the rise of the Industry 4.0 era, the increasing plethora of sensors, data, and the ability to be able to process and use that data is what we believe a gateway to sustainable mine to mill. And so this session is to talk through some of those things. We'll be somewhat guided by the questions, but we have a number of areas and technologies that we can explain. Quickly though, the 5 key areas that we see that tend to surmount proposed challenges for sustainable mine to mill. First of all, the level of resolution of ore body knowledge. A heterogeneous ore body in particular, where there's a lot of variability. It's quite important for that variability to be understood so that when we implement blasting, we match energy to the differences in those ore domains to be able to produce consistent fragmentation. Which brings us through to the next immediate challenge, because even if we do know a lot about that ore body, and even if that ore body is quite variable, blasting tends to be executed on standardized templates. The role of the engineer is a frenetic role, and they need to put blasts in front of hungry digging units and communicate instructions effectively on the ground. So templates tend to be quite standardized. So if we have very variable rock and quite standardized templates, we're obviously going to get a difference in fragmentation results. But when we do that, that doesn't necessarily help us either, because if we don't have a good handle on fragmentation measurement, and if our sampling is quite poor and that data is not available and able to be consumed to help us with better blasting, then that visibility is of course missed. And then the material flows through, which may be well traced in the event of perhaps direct feeding through to a process plant, or may present its own set of challenges when there are multiple sources of ore from the pit, or perhaps sources of ore from the pit that are combined with blended stockpile material from stockpiles that were perhaps blasted and mined quite some time ago. And so in the end, we have throughput through the process plant, which may be quite different to what we expect. And then do we have the tools to be able to go back and reconcile with what happened with the design, with what was actually implemented, and where our bottleneck may be. Was it in the blasting or in the lack of response to ore body knowledge, or was it in fact somewhere in the process plant? And so there are areas that we can talk to of all of these, but perhaps in the audience, if any of this resonates with you, or of course, if there are areas of particular interest that you'd like to explore in discussions through this interactive session, perhaps if you could raise that question or raise your hand now. And I'll ask perhaps a facilitator and Nick if any of those have come up before we continue.
Not so far, Angelo, but I wouldn't mind asking you a question myself that I think would be of general interest.
Sure.
And that is, does more intense blasting, and then obviously, as one would expect, finer fragmentation, does that always result in higher throughput in terms of tonnes per hour?
In general, through mine-to-mill studies, applying higher blasting energy to ore has helped to achieve improved throughput. One of the people who raised the question in the last session pointed out a very good point, which I had missed, of course, that it depends also on the processing. So SAG mills, for example, respond very well to being able to influence fragmentation on the finer side, but other processes that perhaps maybe just ag mills, for example, respond quite differently. So understanding the ore body, what we do with blasting, and the process involved dictates that. But the only other comments that perhaps I'll make is that the ore body itself is typically quite variable. And so having pretty coarse or broad domains and applying blasting it to higher energy as a general rule across the ore domains is not necessarily going to be the best use of energy. It may be a blanket solution, but it's not tailored enough. And in some areas we can waste energy and not get the result that we're after, but definitely in areas where harder ore responds to better fragmentation through the processing, it does help and has proven to do so. So the trick is to be able to simulate that well and understand that, Nick, and also measure it.
Thank you.
Nick, do you perhaps...
So we do have another here from Agus Haryanto from TIS. You have mentioned lack or poor quality fragmentation measurement data. Are there any good tools to capture the blasting fragmentation quality?
Yeah, that's a really good point, Agus. Thank you for raising the question. I might just go to a slide that talks a bit about that. So in mine sites, typically fragmentation at the blast face, or in situ fragmentation, is either not measured or it's measured quite sporadically by manual means. And we don't see much automation. But of course, this is an area where the industry is progressively moving to, and there are fragmentation systems. We in Orica have FragTrack automated fragmentation systems, and there are others in the industry as well. But perhaps to talk about the differences and the advantage. Handheld systems will operated by people. They need access to the face. They can only get that at certain times of the day, and there's only a certain number of images that they can capture and do some of the manual processing that's required in some of those semi-automated methods. So consequently, you're subject to bias errors, not having a whole lot of data points, and therefore not having images that reflect the variability of the ore that we're mining in blasts. There are automated fragmentation systems such as FragTrack, as I mentioned. They are permanently affixed to digging equipment, such as face shovels. They trigger automatically, they capture images automatically, and they process images automatically, which means that we get high sampling frequency rates, good, solid coverage, and very consistent processing. Thanks for the question. Are there any others there, Nick?
No, that was the last one that we've got so far.
Okay. Nick, perhaps I might raise one for you, because we mentioned before, does blasting to higher energy always give higher throughput? And I mentioned that the selective ability to be able to target energy to different rocks is what's important. But how would our users know what type of fragmentation in different parts of their ore give them better processing? How could they model that? How could they understand that?
Yeah, it's a very good area to explore, Angelo, because there are a lot of mathematical models to be able to determine the fragmentation from the blast design and the explosives column and the sub drill and all of these sorts of things. But one of the things that we've done in CRC ORE with the integrated extraction simulator is to kind of turn that formulation on its head and actually say, okay, this is the fragmentation that we would like from the blast. So what is the design that gives us that? And the diagram that Angelo's put up on there is a flow sheet that's been configured in the integrated extraction simulator. And right up on the top left-hand side is actually the blast itself, where we put in the mathematical modeling of the blast. And then it takes it from left to right, and generally going from top to bottom, through the comminution circuits, sag milling, then ball milling, then through to the various flotation circuits that we have there and to the final product. And what we can do is we can look at the entire process and then optimize the fragmentation of the blast, so the very first step, to the optimal output of the entire circuit. So you can actually have as the objective function that you would like to maximize the metal production in the final concentrate, and what would be the right settings in the blast to do that, and of course other settings in the mill. And so that stands the kind of more traditional look at this on its head. So rather than saying, what fragmentation result do I get from this blast design? You say, what blast design do I need to get the fragmentation result that would then achieve the best throughput and recovery in the mill? And I think after the last couple of years, we've refined that and are now rolling that out as an operational decision-making tool.
Thanks, Nick. And I might add a question. Is that just done on a blast by blast basis as you're about to do the blast, or is there a way to understand that across the ore body?
So one of the capabilities of the extraction simulator, whether it's running in simulation mode or optimization mode, is to be able to feed it the entire block model. So if you have your geometallurgical parameters and your geotechnical parameters interpolated into each block of the block model, you can then actually see what the throughput and the recovery would be for literally every block. So very, very high resolution understanding of performance. And then of course, the concentrator changes in design and performance over the years that it's used. So there's also the ability in the extraction simulator to configure different circuits that will get used in the different years. So there's quite a sophisticated ability there to look at the whole life of mine over the whole of the ore body.
Yeah, thanks, Nick. Are there any questions there? Otherwise, I'll pose an area where I get asked a lot of questions.
By all means.
Okay, so one of the questions I get asked a lot is that if we understand what fragmentation needs to be achieved, but we have differences in the ore body, how can we cater for that in blasting? What are the modern solutions that help us with that? And that I might just change my slide here and go back to what I was showing before, which is that variability in the ore body. And so that relates to, well, how can I understand this variability more so, and how do I react to it? And the answer to that is that increasingly there are a number of sensor technologies starting to come to the market that pick up more and more information of the ore body at blast hole level, which is of course a much more granular level than is typically the source data for processing the geological model. It's actually measured data. Right now, perhaps the largest and most underutilized data source for that would be measure while drill data, the mechanical type of data that comes off the action of drilling the holes. Typically, we refer to measure while drill. So in Orica, we've been looking at that and say, well, how can we use that to automate the process of allocating the right energy where it's required to respond to that, to get consistent fragmentation? And that has two elements to it. One is being able to have a connected blast design and control system, so that if I have designs that are issued from the engineering office where there may be differences between different blast holes, that we can effectively communicate that and get it loaded through connected explosives delivery systems in such a way that if I have 400 holes, I don't have to issue 400 different instructions or loading sheets, but I can issue a tailored design all the way through to a truck control system, which will faithfully deliver that design in the field. And that then begs the second question, which is to say, well, if I know that I can tailor a blast for a better result, how do I get that information about the more granular nature of the rock to that design? And again, there's solutions that are enabling the use of data and machine learning from a history of measure while drill data to then apply to newly captured drill data in cycle time in order to be able to affect the blast design. And what I mean by that is to be able to take one source of data, and in the image here, there's a number of them, but let's just focus on measure while drill for a moment, and to be able to capture that off the drills by plumbing them through to, in our case, cloud-supported systems, run algorithms across them that automatically domain and produce the hardness variations in the field. So we might have a geological model that suggests that there is a hard zone, as I've got here with my mouse, compared to a soft zone based on what we have at that coarse model view. Whereas in fact, what we have based on drilling sensors giving us real information is something that's far more granular and textured. And so that can be processed with automated load rules to loading into the field through the smart trucks. And that's technology that's not sort of a 5-year horizon. That's technology that's here and now and enabling those blasts to achieve more consistent fragmentation through tailored blast designs. Are there any other questions which have come up there, Nick?
No, there isn't. And I'm just wondering, Michael, I think, is our representative from Clarendon who is looking after this session. Michael, how are we going time-wise?
We have another 3 minutes.
Yeah, so I was thinking, Angelo, perhaps that last slide where we have the main points of the like of the summary of this session, that might be a good way to end up if we've just got a couple of minutes to go.
Sounds good.
Yeah, for sure. Okay, we may summarize that. In summary, the enabling technologies that are required to enable us to make an end-to-end decision making, they are now available. Nick talked about the integrated extraction simulator, which goes from blasting all the way through to any configuration of processing and blending. That is now available. That can be implemented now, and it can do mass simulations all the way back to the ore body so that we can solve for optimum fragmentation even at a individual block level in the block model. And then the advances in blasting around digitalization and the use of machine learning of historical data, of measured fragmentation, of measure while drill data, and of actual increasing sensor data that's coming from mine operations. That's enabling precision blasting connected through the workflows to connected and smart mobile manufacturing units or explosives trucks, so that we can meter out explosives exactly where they're required to match the ore body characteristics for the best fragmentation. And of course, as I mentioned before, a key enabling technology is being able to simulate that and to simulate that in such a way that it can be used not just for planning, but in operational workflow decision-making. So those technologies are here and now today and starting to be adopted by certain customers and coming together more and more in integrated end-to-end operational workflow solutions. Anything else you'd like to add to that, Nick?
No, I was just going to say, I think that last point that you made there, Angelo, that the enabling technologies are there, and that it's not just simulation, but it's also optimization. And we can do that now on the scale that gives people very, very high resolution understanding of what's achievable with different blasting techniques. That's
right, yes. And in the scale of this topic and time, it's difficult to cover that. But you've seen some preview of the use of data science and MWD data into domaining for blasting. Some quick discussion on integrated blast control systems that take digital design through to connected trucks in the field. A bit on fragmentation measurement and the automation of that. And an area we didn't get to preview, but of course there is also capability in, is the tagging and tracing of ore material from the blast through to the process plant so that you can maintain that traceability through various blending scenarios. All of that add up to components together with end-to-end process simulation and modeling, as Nick described, to enable a more sustainable ongoing implementation of operational mind and mill. To the collaborative facilitator, how are we looking for time, or are there any other questions?
Yeah, is there any questions that everyone would like to extend to Nick and Angelo here? If not, we will proceed back to our main room and proceed to for lunch break. But of course, if you have a question, please take the opportunity to extend your questions to Angelo and Nick now. You may turn on your mic if you have a question, or feel free to write it down on the chat box.
Michael, it looks like we've solved mining.
Yeah, it seems like there's no questions from the rest. So thank you so much, Angelo and Nick, for this for the session. And yep, we will proceed back to the main forum shortly. Just stay put for a while, and my colleague will actually put everyone back to the main.
Thank you, Michael, and thank you to the attendees.
Thank you.
Thank you also very much.
Comprehensive. Thank you, fellas.
Thank you. I'm not sure if people are still on the line in that sort of awkward moment between exchange for rooms, but please feel free to reach out to Nick or myself for any further discussion on any of those elements, or in fact how an implementable end-to-end program could be set up for your own operation. And thank you for attending.
Thank you.
Yeah, maybe Angelo and Nick, would you want to share your email contact over the chat box function over there? And then maybe if there's any questions from the participants, they can actually extend it to you. Or they feel free, they would like to connect with you.
For sure. I'll just put out email addresses in the chat room now. Thank you.
Yeah.
Thanks for that, Michael. It seems like all the technology worked and you had a good set of attendees, so thank you.
Yeah, good to know that. Thank you, Nick.
And it's now a lunch break, I heard you say.
Yeah, we are heading back to lunch break, but we will actually proceed back to the main room first.
Right, okay.
Yeah.
Do we need to do anything to do that, or would we just get taken back when they get reassigned?
We will assign, so you'll be automatically back. We'll move back to the
Thank you.
Yeah.